Hi everybody, going to go over the modern physics homework. I'm just going to really lay out the equations. You can put in the numbers to get the solutions. If there was any issues, obviously contact me. So in problem 1, we're using the de Broglie wavelength of electrons and really relating that to energy and momentum. And so the big idea in this one is we have to be comfortable going back and forth between energy and momentum and make sure we're applying the correct energy equations for particles versus, let's say, light, which is slightly different. So in this momentum one, you're not going to do a simple m times v because you're really not given any information about v. We can use the wavelength and the idea that de Broglie wavelength is related to the momentum by this relationship. So if I rearrange that, I get the momentum is h over lambda. Okay, so you can just plug in the values for lambda, for h I should say, and lambda. Just make sure you convert that to meters so you get the right value for the momentum. By the way, you might be wondering what's non-relativistic. Non-relativistic means that the electron is not moving appreciably close to the speed of light. And that's important because the classical equations for momentum energy would change. And we're not going to do that here. And that's especially important for B. Calculate the kinetic energy of the electron in joules. So there's two approaches you could do. The long approach is probably the approach you might have taken. You could do 1/2 mv squared, where v is equal to the momentum you found above divided by the mass of an electron. And that'll work. A more straightforward one is an equation we derived last year that relates kinetic energy and momentum directly for a particle. And that's Ke is p squared over 2m. That comes from really combining those two equations there. It's just really handy here. So if I use this equation directly, I've got the momentum from above. I can put over twice the mass of an electron, and you should get the same answer in joules. All right, next question, calculate the accelerating voltage. Okay, so you're able to, sorry, I don't know what I'm doing here. You're able to accelerate it the way it is because it has a charge, and charges can be given energy by putting them across electric field with voltage. So anyway, the kinetic energy that you found here is equal to the charge of the electron multiplied by that accelerating voltage. So that's pretty straightforward. There doesn't have to be anything that is figured out separately from there. And then suppose the light, instead of heat, is used to release electrons from the cathode. Okay, so this sounds like the photoelectric effect, right? When you have light come in and you are releasing electrons, you are creating a photocurrent. So the idea there is, in order to accomplish it, the minimum one is you need h times a minimum frequency. And that minimum frequency is equal to the minimum energy that has to be overcome. Okay, and that's going to be equal to your work function. So the minimum frequency to do that is, whoa, that's really messed up, equal to the work function divided by f, and that work function is given at the very top. Okay, so let's continue on to number 2. So I just got basic information. A photon with a particular wavelength, it's emitted from an ultraviolet source. Okay, so calculate the energy of the electron. Pretty straightforward. That's just hc over lambda. You can do that directly. Calculate the de Broglie wavelength. So this is a little bit more involved. All right, where the stipulation that the kinetic energy is equal to the energy of the photon. Okay, so basically we know that the de Broglie wavelength is going to be h over p. So we need to get the momentum of the electron, which has an energy equivalent to what we have up here. Okay, so we got this energy. We're going to use this energy to find this momentum. So we just need a connection between them. And that's, again, where that equation where Ke is equal to p squared over 2m is really helpful. So I can directly connect them. So if I solve for momentum, that's just twice the mass divided by, or multiplied by the Ke, square root of all that. And again, it's the mass of the electron that allows us to do that. So you got to do that in a few steps. And if you do so, you get the 10 to the negative 10th meters. Okay, so then the last one on this part here is the energy that, oh wait, I think I added one, didn't I? I'm sorry, I forgot that I added a problem on C. Okay, so is the energy have the same? The answer is no. So let me show you a little derivation. So to do that, I'm going to try to express the electron in terms of the photon. So let's start with the electron momentum. The electron's momentum, and we're relating it to the energies because that's what's the same. So I'm going to basically go with that same equation where that's twice the kinetic energy times the mass. So all I'm going to do is substitute out the kinetic energy of the electron for the same value for the energy of the photon. So we just need an equation for the energy of the photon as it relates to its momentum. So you could start, so this is the electron right there. So if I want to look at the photon, I mean, the equation is the momentum of the photon is simply its energy divided by the speed of light, c. Now I got that because I started from h over lambda, that's what we do know, and I substitute out the lambda. I can do that in terms of energy because I know that the wavelength is associated with energy via the equation E equals hc over lambda. So if I solve for lambda for this equation, right, and substitute it into here, then I end up, so I take the lambda equation, substitute it into lambda in there, and I simplify and I get that. So I can then say that the momentum of the electron equals twice, there's the 2, so if I go over here, the energy of the photon is Pc, and in terms of the, so that's P of the photon times C times M. And the point is, they're not the same value. Okay, if they were, they would have both P's would be the same. Okay, so the last question is outline an experiment that would show that we have electron property or wave properties of an electron. And this is really important you be able to describe this in outline form, and I'm just going to give you the skeleton form. What you want to do is you want to take a beam of electrons. Okay, it can't be done with one, in other words, and you shine it on, beam of electrons shined or shown, I don't know, shined on crystals, or you could get away with this, a grating, a diffraction grating. In other words, something that indicates a device with many spaces in it that are very, very small. Okay? And then you look, ultimately, why are we doing that? We're looking for interference. That's the classic way of saying if something is a wave or not. Okay? And that's, again, due to diffraction. And then you just finish up the statement, only waves, okay, can interfere with each other. And that's how you prove that electrons have wave-like properties. This was a Davis and Germer experiment. That's pretty important. Let's move on to the last one. And this was just a bunch of algebra where once you get it, things just moved on from there. So the derivation basically comes from the photoelectric effect, which basically says that the kinetic energy max equals hf minus the work function. Okay, and so actually, nope, I'm looking at the wrong thing. Let me redo that. Sorry. So this is not a photoelectric effect problem. This is an X-ray. Oh, this is a Compton scattering. Okay, be helpful if I read that first. So we are basically doing conservation of energy there. We have an incoming X-ray photon, so that's going to be called HF, and then, right, it's going to give the electron kinetic energy. That's the KE we're interested in. And then there's going to be a scattered photon that has a different frequency, okay? And that's a lower frequency because it's lost some energy. So we can just rearrange that and say that's HF or HF minus F prime. Okay, pretty straightforward. Now, determine the momentum, the magnitude of the momentum of the scattered electrons in terms of all those. And yet, once again, we know, since we know the kinetic energy, we can get the momentum by p squared over 2m. So, p is equal, again, to radical 2 ke times m. And so now we can just put in what we have here for KE. So that's ultimately what the final answer is as expressed in the problem we did there. It says determine the de Broglie wavelength in terms of that. Well, de Broglie wavelength is lambda is h over momentum. So the answer is going to be h over this whole thing down there. Okay, so it's just an issue of rewriting all that. And then if the collision happened in one dimension, determine the momentum of the scattered X-ray in terms of all those variables. So this is a conservation of momentum problem. So we have basically, in terms of momentum, we have the initial momentum of the photon. Oops. Okay. All the momentum is there. That's going to equal the momentum of the electron plus the momentum of the scattered photon. So in other words, my the electron's momentum after is simply equal to the initial photon momentum minus the new photon momentum. And then you can just put in all the information, right? This initial momentum would be h over lambda. Okay, and then you can well, actually, right, we want to do it in terms of f prime and that. So let me go rewrite over there. So that's h over lambda, and lambda is going to be speed of light over the frequency. So that's really the only thing that changes, right? I got that right. So this is going to become h f over c minus the answer from here. Okay, so hopefully you're making connections there, and again, we'll try to clarify anything in class.